Okay, thank you very much, Miss Siti. Good afternoon, everyone. Assalamualaikum warahmatullahi wabarakatuh. Hopefully, you all of you in the good health. Now, I will present about GNSS innovation, development, and application in Indonesia. My name is Sony Darmawan. Also, for make this slide, I take slide from our college, from Dr. Catur Rohmana, Dr. Agustan. We are from Indonesia Society for Remote Sensing. Actually, I'm not expert on GNSS, but I try to show and to explain about GNSS activity in Indonesia. Okay, I will start introduce myself. My name is Sony Darmawan, General Secretary of Indonesian Society for Remote Sensing. Yeah, actually I'm before in University of Tokyo also from Wataru Takeuchi Lab, and I'm very familiar with the all speaker as Professor Shibasaki and Dr. Dines and all. And best regard for all speaker and for all participants. First, I will explain about the geospatial on industry 4.0. That one of the important technology is GNSS and positioning, with the facilitators, process, delivery platform, also Internet of Things, artificial intelligence, cloud, wireless and broadband, and big data will give benefit for citizen, business, and government, and especially will give benefit on economy and society. For example, GNSS benefit, I check in some literature. This is in the sample in Europe. Some literature mentioned that about 6 until 7% of the European economy relies on satellite navigation service. Yeah. 10% all space data, and around 60 billion euro revenue expected in Europe, and in the paper say thanks to Galileo and EGNOS, and also in 50,000 jobs affected annual in the Europe. And we sure, and I'm sure, not only in Europe, on the another country like Indonesia, industry and market will increase toward a positive direction. And I will try explain in Indonesia case. In Indonesia case, for example, GNSS innovation in Indonesia, low-cost GNSS positioning technology had significant growth. For example, one of the GNSS installation company in Indonesia can see in the link, this link, potretudara.com. They are developed the GNSS module board called the original equipment manufacturer board, and they and at first the equipment was developed for measurement solution with sufficient accuracy and with an affordable price. On the development, this equipment is often using for in unmanned aerial vehicle or UAV. In this company GNSS module for recording raw parcel data. For example, module for data communication using Wi-Fi, Bluetooth, GSM, also with the micro SD, radio telemetry, also input output to module GNSS RTK, and add some module power bank and have the module antenna. And build GNSS data logger. Before we have the module GNSS, and then give the input output and module for controller on the open source program, and after that can become the data logger, geotagging camera, also this data collector can be used for surveying, drone PPK, stakeout, or machine control. For example, this is GNSS PPK on variety platform. Before we have the GNSS data logger and can be used on the platform drone PPK, boot bathymetry, LiDAR GNSS, and mobile mapping and also for surveying instrument. This is also electronic bathymetry in this company from Catur Aris Rohmana. E-bathymetry is a small radio control for bathymetry and also GNSS module or some with the unmanned surface vessel for bathymetry. Bathymetry is to measure the depth of the water, depth of the river, lake, or ocean. But this is a small platform. Maybe can be used for small river or small lake. Other sample UAV PPK ready, GNSS module PPK and the UAV platform. This is the micro UAV for map production. On the UAV also include geotagging camera and accuracy around the submeter. And also geocam. This is geotagging camera for multi-purpose. For example, collecting point of interest or POE and become POE dataset or database, and it is can be used complement for base map, also for another purpose. This instrument simple, including have the camera, GNSS module, power bank, and antenna, and can be used for multi-purpose also. And then how the market GNSS market in Indonesia. One of the people from Harry Andreas and Sandi Novriansyah mentioned about the summary of GNSS market in Indonesia until 2018. They mentioned on high processing positioning for geodynamic and deformation, monitoring, disaster mitigation, also early warning system, on surveying and mapping for survey network, drone control point, and else. also on navigation and location-based service or LBS for tracking and, for example, on the Google Map, Waze, Gojek or Grab, on maritime for bathymetry and else, and on aviation, flight navigation, positioning, and else, and in other for military, GPS, agriculture, sport, recreation, and else. However, market on navigation, on location-based service or LBS, also aviation is the biggest market in the world. But for this time, I just explained GNSS for survey and mapping be adapted with the Indonesian development. In the recent time, on the survey and mapping in Indonesia, our president regulation regarding acceleration of one map policy on or OMP. On the one map policy is mean one georeference, one version, one custodian, one geoportal, one standard, and also one database. And of course, for one georeference and one database, GNSS has important contribution. In the president vision of using the one map policy to resolve overlapping utilization and land conflict will require massive effort. And also request for base map in Indonesia, base map, for example, for one map policy, this is required base map on 50,000 scale, and this program new hardware development or maritime toll road 10,000 scale, village mapping 5,000 scale, detailed spatial planning 5,000 scale, also for pitland. For pitland, this is required base mapping 2,500 development on the for development of special economic zone on an industrial zone, required base map 1,000. For smart city development, required base map 1,000 scale, and acceleration of land registration required base map on 500 until 5,000. And the reality in Indonesia case, base map in Indonesia case, Indonesia country is still very lack. For example, base map on the large scale, on the 5,000 scale, this is in the red color. This is still a small area in Indonesia, maybe just 1 until 2% compared on the overall in Indonesia country. It is very challenging that Indonesia government has a target, has a base map on the large scale on the 2024, and remote sensing technology and photogrammetry, LiDAR will be used for the mapping for whole Indonesia country. And of course, GNSS has important contribution. And contribution GNSS for very high resolution satellite image. For example, we have the data in very high resolution satellite image, and then for processing, we need the GNSS is used to establish ground control point or GCP for auto rectification of aerial photo or satellite image. Maybe usually based on GNSS rapid static surveying method. On another case, GNSS for photogrammetry or mapping also, GNSS used for establishing the ground control point. Based on GNSS, differential post-processing static positioning. Also, minister regulation about the village mapping in Indonesia, and of course, GNSS has important contribution. Actually, in Indonesia, have 80,000 village, and they need the map for development planning. And GNSS-based positioning, surveying, and mapping will play important roles for sustainable rural development in Indonesia. Also, Presidential Instruction Number 2, 2018, concerning an acceleration of complete systematic land registration or PTSL, instruct the Minister of Agrarian Affairs to make regulation and take steps to accelerate the achievement of PTSL or systematic land registration, which covers the process of land ownership and control. The target until 2024, that land registration around 15 million parcel. That is Indonesian program and policy on surveying and mapping, and GNSS very important contribution for survey and mapping in Indonesia. And for the now and May future direction, as we know, the future direction of development city toward to smart city. Position and navigation information is very important on the human life, and of course GNSS has important contribution. And the next maybe good for discussion about the society 5.0. On the society 5.0, where information be used for guidance of all our activity. And I believe GNSS is important tools for supporting society 5.0. Okay, this is conclusion for our slide. GNSS research study, industry development and market in Indonesia are growing very fast in a positive direction. And GNSS system is promising technology and important contribution to various aspects of society. And we believe the GNSS market in Indonesia will be the biggest around Southeast Asia, in even in the Asia Pacific. And on the academic perspective, open collaboration needed for accelerating of benefit for better human life. That's all. Thank you very much for your attention. Thank you, Miss Siti, Dr. Glynn.
Thank you, Dr. Sani Darmawan, for the enlightening lecture. Now we're entering webinar 3, and the webinar will be led by our moderator, Dr. Lin Yola. Please welcome Dr. Lin Yola.
Thank you, Ms. Siti. Ladies and gentlemen, I'm Dr. Lin Yola. I will be the moderator for the webinar discussions for today. Let me remind all of us again that our big theme for this webinar today is the GNSS applications for academics, commercial, and policymakers. After the presentations from all of the speakers, we will have Q&A sessions. We will choose some questions from the registration link and also the online questions. To our participants that have any question regarding the discussions, please post your question and to whom the question is addressed to in the Q&A chat room in both Zoom and YouTube. And the attendance link will be also shared in the chat room. So let me introduce our speakers for today. We have Dr. Yize. He is from the Tokyo University of Science and Technology, Otomsat, Japan. He is currently doing the research that focus on the multi-GNSS precise point positioning and GNSS bias analysis. In these sessions, he will talk about introductions to RTK and RTKLIB. The second one, sorry, Dr. Yize, how are you today?
Yeah.
Yeah.
Thank you.
Yeah, thank you. The second one, we have Mr. Hideshi Kakimoto. He's from the GPAS or Global Positioning Augmentation Service Japan Corporations. In these sessions, he will talk about introductions to Madoka. Hello, Mr. Kakimoto.
Hi, Dr. Lin.
Hello, yeah. Hello, the next one is we have Dr. Dinesh Manandar. I think if you attended the webinar yesterday, you already know that he's the project associate professor in CSIS, Center for Spatial Information Science, University of Tokyo. In these sessions, he will talk about the low-cost, high-accuracy system based on RTK and Madoka. Hello again, Dr. Dinesh.
Hello, thank you.
Yeah,
thank you for introduction.
Thank you very much, Dr. Dinesh. So I would like to let all of the participants know, especially for those who didn't attend the webinar yesterday, that for yesterday's sessions, we did have a few topics about, most of them are about the introduction of the GNSS or the application of the GNSS system for research, academics, commercials, and also the private sectors. But for today, we are having the further details discussions on those topics. So the topics I already mentioned just now, mostly about RTK, RTKLIB, Madoka, RTK and Madoka, something like that. So before I call the first presenter or the first speaker, maybe I would like to invite Dr. Dinesh to give some briefing about the webinar 3 today. Please, Dr. Dinesh, the stage is yours.
Yeah, thank you very much. So today we have the second day of webinar, and this webinar today we are going to give you a little bit more technical information on how to process data for high accuracy. So this is the main theme or objective of this webinar. But in this webinar, we are not going in very technical details. So we'll just show you some available softwares, hardware, and other applications. And today we have Dr. Ize, so he will be talking mostly on the RTK and RTKLIB software. He will tell you how to use RTKLIB, just a very brief introduction, just outline. So we just want to let you know that these softwares are available so that you can buy very low cost $50, $100 receiver, and you can get 10 or 20, 30, 50 centimeter accuracy. Then we have a Madoka, which is very new. Even for us, it's very, very new. So we are doing lots of tests and trials on this. And we are now going to promote this in Asia, basically. So Mr. Kakimoto, he will be talking on this, also again, the outline. And finally, I will talk on some softwares that we have developed based on Android or Raspberry Pi for these low-cost systems for RTK and Madoka. So I'll show you some software examples, and we'll also share some of these devices to the universities in Asia that we have collaboration with the universities. So that's all. And so I would like to welcome our speakers. So maybe Dr. Ize first. Thank you very much.
Thank you very much, Dr. Dinesh. Dr. Ize, please. You have around 35 to 40 minutes. Thank you.
Okay, thank you very much. I'm going to share my slides. Okay, good afternoon, everyone. I'm Ize Zhang from Tokyo University of Marine Science and Technology. So today, my introduction mainly talking about RTK and RTKLIB software. And here is the contents of my presentation. So first is some basic concept of RTK. And as yesterday, Dr. Dinesh have already introduced how GNSS works. And if we have 4 satellites, we can decide our position of our receiver. So now GNSS positioning have different kinds of positioning technique. There are mainly 2 types. One is point positioning, and the other is relative positioning. So for point positioning, it can apply it in worldwide area and very easy to use. And for relative positioning, as we have it's relative to a base station or some base stations, so it works only in local areas. And for point positioning, we usually use 2 kinds of techniques. One is SPP, single point positioning. The other one is PPP, which is precise point positioning. And our next 2 speakers will also talking about this PPP technique, especially for the Japanese Madoka service, which is also a kind of PPP. And for relative, we have differential GNSS and RTK. For DGNSS, use the pseudo-range observation, and the RTK, we also use the carrier phase observation. And as yesterday, we also know the course. The course is a kind of network RTK, which means we have not only one base station, we have a lot of stations in the local area. So these reference stations can expand our service area. And recently, with the combination of RTK and the PPP technique, we have PPP RTK technique, which it can use for a wider area, and can also get a similar performance with RTK. And the Japanese CLAS service is also a kind of PPP RTK service. So this is some GNSS positioning techniques. And today we are going to focus on RTK. But before introduce RTK, we should first start from GNSS observation and errors. These figures show the GNSS errors, and we have pseudo-range observation from the satellite to receiver. We can get this information. And during the transmission of satellite signals, we have satellite clock offset and the satellite orbit error. And when the signal transmits into the space, we also the signals also suffer from ionospheric delay and the troposphere delay. And for the receiver side, we also suffer from some receiver clock and the instrumental delay, and also maybe multipass errors. So we have so many different errors. So for the single point positioning with pseudo-range observation, we can get this observation equation, which includes most of the errors. And using this equation, and we have more than 4 satellites, and we use some filters like common filter, we can get our position. So this is how SPP works. And for differential GNSS, it's an extension of SPP. And because if we have a base station, and if it's not very far from your receiver, these two stations have a similar error, almost similar error from the satellite side and the atmosphere side. So by setting up a base station, we can use this station difference strategy to remove these common errors. So this is a basic theory of DGNSS. And for DGNSS, we also usually use the pseudo-range observation. And what I should point is that pseudo-range observation is around usually more than 1 meter's noise. So the accuracy may be not good. And here is an example of a comparison of SPP and the DGNSS. So you can see that the blue point is the DGNSS result, and these numbers are the standard deviation of SPP and the DGNSS. We can see that when we have a base station, we can improve our positioning error with a smaller standard deviation. So these two techniques are all based on pseudo-range. And if we use the carrier phase observation and similar as DGNSS, we get the RTK technique. So this technique also uses the base station, but we have a more precise carrier phase observation. So in addition, we can fix the ambiguity of the carrier phase. So we can get a very precise accuracy of our coordinate in about, for example, 1 centimeter accuracy. And the reason we can get very high accuracy from RTK is that we have a very precise, accurate carrier phase observation compared with the pseudo-range. And we can eliminate the errors from satellites and the atmosphere using a base station. And we can also fix the ambiguity of the carrier phase. So that's why we can get this high accuracy from RTK. And here is the comparison of the previous GNSS result with the RTK, which is shown in the green, green color. You can see that it's just like a very small point and maybe at less than 1 centimeter level. So compared with GNSS, we can see how accurate we can get from RTK. So RTK is a very precise technique to get our position. So to use this RTK technique, we are going to introduce the software of RTKLIB. The RTKLIB is open source software, and you can download from the website. And this software is developed by Mr. Tomoji Takas at our university. And the latest version is 2.4.3b33. And the RTKLIB have various functions. For example, it supports multi-GNSS, including except the India's INSS, and it supports many different kinds of positioning modes. For example, the SPP, DGNSS, RTK, and PPP, and it supports many different formats of the data. For example, we usually use the Linux RTCM or the data we get from uBlocks or Java Substantial. You can also use your modified RTKLIB, use your own receivers. And it supports the real-time communication for the real-time positioning, which is very useful. And it supports many functions. So if you want to develop your own software, you can use these functions, and it's much easier to have your own software. And so these are the GUIs and the CUIs included in RTKLIB. You can check it in detail. So this is the package of RTKLIB. And if we just want to use the software to process the data, we can find the files on the folder of bin. And this is where we can download RTKLIB. It's on GitHub, and this is the website of RTKLIB. You can check it later. And when we turn to GitHub, you can see this page, and you can download this one. This is just the binary files, which means you can run RTKLIB after download these files. So this is an example. If you download RTKLIB, when you open this binary folder, you can find the file of rtklaunch.exe. Then you can find this figure like this, and there are different functions or tools for RTKLIB, and this is the some example of these tools. For example, RTK plot, you can plot your results, and RTK post, you can process your data by processing, post-processing, and RTK Navy, you can use for real-time positioning, and some other GUIs, you can check it in detail by yourself. So if you want to know the detailed meaning or algorithm about RTK or PPP, you can check the manuals of RTKLIB, which is also available on the website. So next, I'm going to show some example of how to use RTK from RTKLIB. And so as we mentioned, we have the this figure when we open RTKLIB, and this is where the RTK post exists. And if we click this, we can get the RTK post. So RTK post is post processing, and it supports not only RTK, but also SPP or PPP, as we said. And here is an example of how to process RTK using RTKLIB. So you can see that in this rectangle, we only need to input our files, including observation files from our lower station and our base station. And we can also input our files of satellite and the clock, which is sometimes the navigation file from the receiver, or the precise files from some other organizations. And for RTK, we just input the navigation files. So it's like this. And after we input these files, we can change some settings to use RTK. So this is options to modify our settings. It's like, here is an example of how to use RTKLIB. And the other parts are the default settings of RTKLIB. And to use RTK, we should change some settings in this rectangle. So this is just some basic settings of RTK. For the other settings, you can check the manual and try it by yourself. And after we have finished these settings, and when we can execute this RTKLIB, and then we can get our results. It's here, and if we plot, then we can get a result like this. For the left figure, this is the result of RTK for all solutions, include the fixed solution and the float solution in the orange color. So, and we can, this is a GUI of RTK plot. If we can show only the RTK fixed solutions in the right figure. So if we check the accuracy, we can see that the standard deviation is less than 1 centimeter in each direction. So it means that when we use RTK, we can get a very high accuracy. And of course, this is an open sky, very open sky environment data. So we can get a better than 1 centimeter accuracy. And so this is just an example showing how we change different settings of RTKLIB to get a better accuracy of the solutions. So for example, if we change the SNR mask, which is signal noise and ratio, and we can get a better solution with the same data. So this figure shows if we set this SNR mask, we can improve our fix rate from about 93 to 97, something like this. So for some other settings, you can try by yourself. And RTK post is just for post-processing. And if we want to use the real-time RTK or PPP, then we should use another tools, RTKNavi. So RTKNavi is here. And when we go into RTKNavi, it's the GUI is like this. And we need to have some other settings because we need to get our real-time data and real-time correction data from the base station. So we need to have some settings of the input streams. So here shows how we change the input setting. And here we use untrip client option. And we have our, if we have our untrip account and untrip ID, we can set our settings. And also for the base station, have a similar setting. And this is for the input setting. And for output setting, which means we need to output our output results or the observation data. We can set our output settings. And this is two different settings from RTK post. So another one is the options, but this option part is totally the same as RTK post. So I will not go in detail of this RTK post setting list of these options. And if we have set our settings correctly, we can get our RTK results. And from the left figure, we can see that here is a solution indicates it's fixed. And this means we have get the RTK fixed solution. And for sometimes it's not always fixed. And when it's not fixed, here shows the float solution. So we can check. So if we want to show our result, here it's we can click the plot button, and this is the real-time result of our RTKNavi solution. And here, similar, the green one is the fix, and the orange one is float solution. So you can see that this grid, each grid is 1 centimeter. So here you can see how accurate we can get from RTKNavi. So this is an example of showing how RTKNavi works. And here it's additional information, because yesterday someone asked the difference of RTKLIB and this software native. So these software have different functions. I have listed here, but this software is only for post-processing, similar as RTK post. And if you want to do the real-time positioning like RTKNavi, but this software doesn't support. But for the accuracy part, and maybe this software have a better accuracy and more functions for post-processing regarding RTK or PPP. And so you can find more detailed information from this website or from GitHub. So this all my presentation, because we are not going to have detailed technique algorithm of RTK. So it's just a general introduction of RTK and RTK Navy. So that's all my presentation. Thank you.
Thank you very much, Dr. Yize. Yeah, I think there are a lot of significant points for us to discuss during the Q&A sessions later. And there are some available questions for yourself already.
Yeah.
So yeah, we will discuss later during the Q&A sessions. Thank you very much again for the comprehensive discussions. So let me call our second speaker for today, ladies and gentlemen. We have Mr. Hideshi Kakimoto. He's going to talk about introductions of Madoka. Mr. Kakimoto, are you here?
Oh, yes, may I
Are you ready? Yeah.
Screen?
Yes.
Okay.
You may please share the screen.
Yes,
Yeah.
I think we can see my slides.
Yeah, we can see it very clear now.
Okay.
So you have around 40 minutes from now.
Okay.
Mr. Kakimoto, the stage is yours. Thank you.
Okay, thank you. Good afternoon, everyone. My name is Hideshi Kakimoto. So first of all, I'm deeply grateful to all organizers of this webinar for giving me the opportunity. So, okay, at first, please let me introduce myself briefly. I am in charge of the engineering department manager of Global Positioning Augmentation Service Corporation. So this is a very long company name, so please call us by abbreviation GPAS, GPAS. So now my company GPAS is providing a data distribution service to improve the accuracy of satellite positioning. So in my presentation, I'd like to introduce this service, and I'd like to show you a simple demonstration of positioning using our service. So now GPAS uses technology so-called Madoka, M-A-D-O-C-A, Madoka, to generate augmentation of GNSS positioning. So Madoka is a processing tool developed by JAXA, Japanese Space Agency, to estimate the precise satellite orbit and clock. I will explain a little about the principle of improving positioning accuracy by applying this technology. The accuracy of satellite positioning can be improved to 10 centimeters by applying augmentation of Madoka. And the augmentation is composed of satellite side collections. This collection term is also known as state space representation, SSR. The figure below shows the main sources of error involved in satellite positioning. So in previous presentation, Dr. Ize has already explained that, but please let me explain again just briefly. To calculate the position by satellite system, first we need the exact position of each satellite. Position of satellite is transmitted from each satellite itself as orbit information. However, its accuracy is only about 1 meter. So this orbital error affects the positioning accuracy of the observer. And in addition, the error of the satellite clock also affects, and also the bias of the signal from satellite affects the positioning accuracy. And then other error sources are signal delay caused by ionosphere and troposphere, through which the signal passes from the satellite to ground. On the ground side, the multipath noise of signal also affect the position. As this figure shows, there are various error factors in satellite positioning. Of these, the error factor on the satellite side will be corrected by Madoka. So the ionosphere and the troposphere are outside the scope of Madoka. So these are corrected by observer's positioning process. In case of general satellite positioning without Madoka, the accuracy is a few meters like this. And in case of augmented positioning by Madoka, that is improved to 10 centimeters by correcting satellite side errors and estimating ionosphere and troposphere by user's data. The method of this positioning is generally called as PPP, precise point positioning. So next, please let me introduce how to start PPP positioning and its positioning performance. So positioning with 10 centimeter accuracy is available by using Madoka augmentation and PPP processing software and GNSS receiver with antenna. This receiver must be able to receive two frequencies of signal, L1 and L2. So most of popular GPS receivers, such as built-in smartphones, can only receive L1. So I think L2 receivable type will be high-end models. So in the next presentation, I think Dr. Dinesh will introduce a low-cost and high-end L1, L2 receiver. So anyway, requirements for PPP positioning are augmentation message and software and receiver. So you can use RTKLIB for PPP processing software. And for GNSS receiver, receiver with built-in PPP software also available. This type of receiver is provided by Magellan Systems Japan. If you are interested, please refer to this URL. This is Magellan Systems Japan. So this is the configuration of PPP positioning. And on the other hand, there is another processing method called PPPAR, PPP with ambiguity resolution. So by PPPAR, positioning accuracy can be further improved like this result. VGPath is providing a software to enable PPPAR positioning. So for this graph, the horizontal axis is time, and the vertical axis is positioning result in 3 dimensions: east, west, north, south, and vertical. And in this case, positioning target was not moved, stayed at 0 points. So the value of vertical axis means positioning error. So, and the color of the graph indicates whether the ambiguity was fixed by PPPAR positioning. So green shows the ambiguity fixed. So please understand the accuracy is higher when the ambiguity is fixed. So in green color, accuracy is higher. Also in PPP positioning, so you can see initial convergence is required from the start of positioning until 10 centimeter accuracy is obtained. So this part, orange color, is almost initial convergence. So this is because it takes time to estimate the error of ionosphere and troposphere using observers' data, as explained in the previous slide. Okay, so that's why we need convergence time. And after the convergence, you can see the accuracy is less than 10 centimeters. So in this case, the performance of this positioning is approximately 30 minutes of initial convergence time and less than 10 centimeters of accuracy, and approximately 10 minutes of time to fast fix. Time to fast fix, TTFF, I mean this time. So the color is turned from orange to green. This time is TTFF. And so next, please let me explain the technology for reducing the convergence time, so-called localized augmentation. In the previous slide, I mentioned that PPP positioning requires 30 minutes of initial convergence time. So this means that you have to wait 30 minutes after turning on your GNSS receiver until you get 10 centimeters accuracy. So I understand this property is difficult to use for many applications. So we are also experimentally providing localized augmentation with Madoka augmentation to improve the initial convergence time. So the principle is very simple. If you can use another GNSS data other than observer's receiver to calculate the error of ionosphere and troposphere, so the calculated error using another data can be applied to observer to start positioning. So this another data should be supplied from continuously operated local station, such as the GNSS station network in Indonesia, inner cores operated by BIG, for example. So in this case, the observer doesn't have to wait 30 minutes by applying the correction value of ionosphere and troposphere calculated by local station. So please note that the distance between the local station and the observer must be within 30 kilometers because ionosphere and troposphere are in different states depending on the region. So that's why we need to do positioning within 30 kilometers. So this graph shows the positioning result by being applied localized augmentation. For reference, the results without localized positioning is drawn in gray line. So you can see the initial convergence time is reduced in case of applying localized augmentation. So the initial convergence time was approximately 1 minute, and also TTFF is about 1 minute. So positioning accuracy is the same as the original results after convergence. Sorry. So I think it will be easier to understand by confirming actual positioning. So I'd like to show a very simple demonstration from now. Now I will show PPP AR positioning using GNSS data from the observation station in Japan. These stations are operated by Japanese Geospatial Institute, GSI, as a part of their CORES network, so-called GeoNet. So from now, I will show two types of positioning. One is PPP AR positioning using the data of station 93032 located around here. And another is PPP AR with localized augmentation using the same data, station 93203 as well as 32. And the localized augmentation is generated from station 93026 that is located at 14.2 kilometers away from the positioning station. Okay, so anyway, I will start sorry. Okay. Just a few minutes. Sorry. So I'd like to use our own software for positioning. The software name is GSOK. So this software is customized from RTKLIB. So now I start the software. Okay, and as well as the graph shown on the slide in presentation, this is a positioning of fixed station. So the position result must be 0. And values in vertical axis means positioning error. And horizontal axis is time in GPS time. So I think 7 hours earlier than Indonesia time. So the graph shows the east-west, north-south, and vertical result. And the vertical axis is plus minus 1 meter. And the plot number 1 is normal PPP-AR. And plot number 2 is PPP-AR with a localized augmentation, localized augmentation. So each position is calculated every second. So number 2 seems to be already converged and ambiguity fixed because it is green color. So the accuracy is less than 10 centimeters. And number 1 will gradually move to 0 in 30 minutes. So this is a convergence time. However, the accuracy is already less than 50 centimeters in horizontal. Vertical accuracy is a little bit worse than horizontal. Okay. So this is the actual positioning result. So let's change the graph type. So this is a horizontal plot. So station 93032 is located at the center of graph. And number 2 is calculated position by PPP-AR with localized augmentation. The accuracy is within about 5 centimeters. So next, I'd like to show you messages of localized augmentation. Sorry. So this is a message of localized augmentation generated from station 93026. So localized augmentation is composed of ionosphere collection and troposphere collection. So this message is calculated from 93026. And the message, so this message TROP is a collection of troposphere delay, and this message ION is a collection of ionosphere delay. So these values mean delay of signal from each satellite. So for example, in this case, GPS number 5 and azimuth elevation and 0.3023 is the delay of ionosphere. So this is a localized augmentation message. Sorry. Okay. So, okay, so next I'd like to briefly introduce the positioning software. Just briefly. We customized RTKLIB to enable PPP AR and applying localized augmentation. So I think standard RTKLIB works just for PPP. I think so. So the interface is almost the same with RTKLIB, but this software does not have GUI, graphical user interface. All configurations are written in the configuration file in text. Like this. So PP positioning mode is PPP kinematic, and ambiguity resolution mode is fixed and hold up and so on. So almost all parameters are the same as RTKLIB. Okay. Okay, so this is just a simple demonstration. I try to go back to the slide. Okay. So next, please let me introduce the mechanism of generating. Sorry, pointer. Generating augmentation message mechanism of that. Augmentation messages of Madoka is consisted of satellite orbit collections and clock collections and signal biases. These collections is calculated from global GNSS observation data. Currently, GPass is using IGS data to generate Madoka message. So, like this figure, by using 4 or more GNSS observation data, including the same satellite data, we can calculate the satellite position and the satellite clock error. So this principle is similar with the satellite positioning using 4 or more GNSS satellite data. And most of satellites are moving on global orbit. So that's why we need a global GNSS observation network to calculate the orbit and clock corrections. So, and now GPass is providing collections of GPS, excluding block 3, and GLONASS, and QGSS number 1. QGSS number 2, 3, 4, and Galileo will be supported by 2022. So, as I mentioned, the GPass is now commercially distributing GNSS augmentation message using Madoka. This is our service menu. We are providing Madoka message excluding FCB as a basic service. So FCB is carrier phase bias, which requires for PPP AR. But the basic service is enough for PPP, normal PPP. And also, we are providing full message, including FCB, for users who require PPP AR. And ephemeris service is a download service of post-processed message. That is better accuracy than real-time service. And this figure is a sample configuration for utilization. To receive augmentation message via the internet, you need a communication device such as a smartphone. And GPass is also providing Madoka message from QGSS as an experiment service on L6E channel of signal. So augmentation message is equivalent to basic message shown on the previous slide. It is provided free of charge from QGSS. So the figure shows visibility of QGSS. Maybe yesterday, Mr. Kogre introduced that. So I think Indonesia is the best location to receive the signal of QGIS. And the next slide is GNSS augmentation message format. So Madoka message conforms to RTCM SSR standard format that is proposed in 2013 to 2014. So for internet service, messages are provided every second. But some values are updated on longer cycle, but the values are provided every second. For the QGSS service, the messages are a little bit decimated because of the limitation of bandwidth. However, the accuracy of positioning is the same with the internet service. But maybe initial convergence and TTFF is a little bit longer because it takes maximum 30 seconds to receive full message. And next, I'd like to show the difference between Madoka positioning and RTK. So this table shows the difference. So RTK is more accurate compared with Madoka PPP, but the accuracy of PPP is also around 10 centimeters. And the big difference is convergence time and service coverage. So as I explained, positioning using Madoka requires a longer convergence time. But however, it can be improved by localized augmentation to almost the same level of RTK. And regarding to the service coverage, Madoka message is location independent because it is just satellite side collections. So it can be used worldwide. But localized augmentation and RTK have location limitation because these positioning must be performed within about 30 kilometers from the reference station. So those are big difference. And also, please note that each coordinate system is different. The positioning calculated with Madoka is absolute position based on ITRF. And on the other hand, the position calculated with RTK is relative position from reference station. So this difference will affect how it is used for applications. For example, relative position is, I think, it is useful for the local survey. So, and absolute position may be useful for the detection of global cluster movement or amplitude caused by an earthquake and so on, I think. So there is a difference for the utilization. Okay. So this is almost a conclusion. So other than observation data of plate tectonics, PPP and PPP-AR will be, I think, very useful in many applications, such as positioning of global mobilities or machineries operated outside of Quartz network, or marine observation, and so on. So I hope you will try Madoka positioning and try to apply it to your applications. So that is almost all of my presentation, but I'd like to show, if I have time, sorry, I'd like to show this graph again. Okay, so it takes about 20 minutes. So normal PPPR is moving to almost zero, almost less than 10 centimeters. So, okay. So this is the difference between the normal PPPR and using the localized augmentation. Okay. sorry. So that's all of the presentation. Thank you very much.
Thank you very much, Mr. Kakimoto, for the very solid discussions just now. I think, yes, again, we have a lot to discuss later during the question and answer. There are also already some questions available for yourself. Yeah,
Okay.
please stay with us until the question and answer sessions.
Yeah.
Thank you very much again.
Thank you very much.
Yeah. The next one, last but not least, let us call Dr. Dinesh Manandar. He is going to talk about the low-cost, high-accuracy system based on RTK and Madoka. Dr. Dinesh, are you set?
Yeah.
Yeah.
So
Please,
let me share my
your slides.
Okay. So you can see my slides now.
Yes, we can see it. Maybe you can help us to make it full view, please.
Yeah, I will do that.
Yeah.
Let me stop this video.
Thank you.
And, okay.
Yes, please. You have around 40 minutes, 40. Thank you.
Okay. So thank you very much for everyone attending this webinar today on the low cost, high accuracy receiver systems. So I will present basically on some of the receiver systems and software we have based on RTK and Madoka. So you already heard what is RTK and how to do RTK, what type of software and hardware exists by the previous speaker. And also from Mr. Kakimoto, you heard a very detailed, also the demo for Madoka. But the receiver he has is it's a bit expensive at the moment because of the not so much production, not so much buyers. So if there are many, it will be cheaper, but we already have some prototypes for low cost. So I would like to show those things today. So before, I think we have a poll somewhere. So I don't know whether we can put that poll now, but anyway, I just want to know how much do you think the price of a GNSS receiver? Okay, so this is a question to you. So you, when they put the poll, I think somewhere later, you can answer and see. Okay, so can you select these answers? How much it costs?
Yes, it's already
Yeah.
displayed. Yeah.
Yeah. So can the participants select how much do you think?
Yes, they
Okay.
already.
Yeah, they are selecting. So please have a few more seconds. So please be quick. We want to proceed for the. Okay, and how much you want to pay? Question one is how much it costs, and number two is how much you are ready to pay. Whether you want to pay just a few $100s or $10,000 or more. Okay, so okay, still there are people entering the answer. Okay, I think it's almost done. Okay, we stop here. Okay, we stop the poll.
All right.
Okay.
Thank you.
Okay, thank you. So I can see, so there are so many who said more than $10,000. Oh, it's like almost 33%. And other 30%, they say between $1,000 to $10,000. Yes, that's the price today. So it's very expensive. And if you really need a very high end with all the signal, it costs more than 10,000, sometimes goes up to $30,000 with a very good antenna. And that's not possible for everyone to purchase. Okay? In the laboratory, in the university, it's very difficult to purchase $30,000 receiver, maybe 5 units for the students to do the training. It's not possible. But you see, you know it costs more than 10,000, but you don't want to pay more than $100. Okay, it doesn't help. Okay, it doesn't work. But we need to find out the solution ourselves. So this is what we do. Okay, so I close this poll. So this is my question to you. So how much we already have this poll and we know how much you want to pay. And also you almost know how much it costs. Yes, that's true. Okay. And what accuracy we can get from a receiver, millimeter, centimeter, or a few meters, 10 to 30 meters. Okay. So if you don't do any accuracy correction or some processing, so this is about the GPS is guaranteed for about 10 meters. But we can have even a centimeter or millimeter. There are different way of observing the data, different way of signal processing you saw already in RTK. And also we have a Madoka. So, oh no, we can close this poll. Okay. And, but it's not only the cost, also it depends on the application. So you have to know what are you going to use for, what are your applications, whether you are going to use for geodetic applications. Okay, then low cost is not a solution for you. You have to go for a high-end receiver, so that will cost you more than $10,000. But if you are going to do some GIS survey or collecting some data, yesterday somebody asked, okay, whether we can use to collect some social data or anthropological data. Yes, you can do, and you don't need a $10,000 receiver. That's too much for you. You don't need that all these capabilities. You just need a latitude, longitude, and time data. So you need a very simple receiver, and that's just $100 or less. And how are you going to log the data? Whether you are logging on a static mode, you take a point-by-point survey, or whether you are going to put on a machine, like a car, tractor, or you put on some robots. Okay, this means whether it is, held by a human or put on a tripod or is on a machine. Okay, it's a different way of logging the data. And also a very important part is whether you want to do real-time positioning or post-processing. I mean, you just log the data, you come back to the office and you do the processing for high accuracy. So all this makes the receiver very different and the cost varies a lot. So if you just do the post-processing, so you really don't need to have all these real-time facilities in the receiver. That will increase your cost, like a radio, Wi-Fi, all these things, and also the memory and CPUs, the computer, the receiver. So this will all add up the cost. So you don't buy unless it is really necessary. But sometimes your applications are very mixed. Sometimes you have to do real time, sometimes post-processing. So probably then you have to select the receiver that is capable to do real-time processing. So what I mean by high-end survey-grade receivers means that these receivers are capable of logging the different types of signals in different frequency band, at least L1 and L2, two frequencies, a minimum for RTK or Madoka. We need have a carrier phase observation, output, carrier phase output, and some other raw data. And also today, the receivers are multi-system, GPS, GLONASS, Galileo, and this is Galileo, okay, GLONASS, and Chinese Beidou system, Japanese QGSS, and Indian NAVIC system. And then you have option to choose which frequencies you want. So normally we are good enough for only with L1 and L2 for RTK and Madoka. But there are different purposes of using different types of signals in different environments. So if you want to buy a high-end receiver with all these frequencies, I think the price will go more than $20,000 for a very high-end receiver. Okay. So when we say low cost, means normally it's a single frequency L1, E1, B1, so they have the same frequency band. But nowadays we can have multi-GNSS, so GPS, QGSS, GLONASS, Galileo, Beidou, all embedded. So mostly at least 3 systems GNSS we can find today, even a very low price. Okay, so we will have at least 3 or more today, even with the low price systems. Okay. And already in the market, so we already have a very low price receiver system that has L1, L2 or L1, L5. So in the first talk, we saw some modules there. So some of those modules, they already have L1, L2 or L1, L5. And this is now coming up. And also in the smartphone, you already have L1, L5 GNSS receivers in some of the smartphones already from Broadcom and Qualcomm. And very recently, Sony in Japan, they have already released L1, L5 GNSS chipset. So more and more new products for the mass market is coming up. That means the price will be going down. Okay. So today, this low cost is about $200. And basically, it's a L1 band. But also we have some receivers. We also have L1, L2 or L1, L5, but L1 is very common. And the total cost is about $300, including antenna and all necessary hardware and software. So, but I think this $200 is still expensive. And my target, this is my personal target, to make it less than $100. So unless we have a receiver that is within $100, I don't think we can use it in Asia. So many universities, training centers, or even small users, they can't afford a receiver that is more than $100. So the target must be less than $100. So this is my definition for low cost. So the price. So when you go to a shop, you should be able to buy for $100, including receiver, antenna, and other things, okay, except the battery, the power, because that's a separate. And accuracy should be better than 1 meter, 100 centimeter. So it should provide better than 1 meter accuracy. And it should be very, very small, not 1 kg of the huge device. So it should be, I would like to have 100 gram or less, okay, including everything. But this is very challenging. At the moment, it's not possible. So this is what I mean, including the antenna. But antenna itself is now about 300 grams or like that. So it's big as well. So we want to make very, very compact, very small, and high accuracy and low cost. So this is extremely difficult. But we are, I think, somewhere in the middle. So the cost is about 300. Accuracy is okay. This we can have even 30 centimeter now. This is still a problem, not possible, but we expect early next year, this one. Okay, I will show you why this is possible. Okay, this is something related with the antenna. So if we can have very good antenna and very small antenna, so we can do that. So many applications, they require low cost, small size, and low power. It's not only the cost and size, but also the low consumption power. So when you go to the field, you should be able to log the data for maybe at least 8 hours, because this is the standard working hour. So you should be able to log the data for many, many hours in the field. It's not like that. You log the data for 2 hours and your battery runs out. It doesn't help you. So we are looking at a receiver or a system that lasts for multiple hours, at least 8 hours, if possible, at least 12 hours. Okay, so this is what we need, and still the cost is $100. This is the target. It's not possible at the moment, but this is the target. And whether this is possible or not, so this is what we are now doing, different types of tests and different types of architecture with the commercially available receivers, because we don't develop receivers ourselves. We just buy whatever available in the market, the chips or modules, and we integrate and make a package. And what we can do is, or what we have to do is to make a software that can control the receiver so that it will take low power, give you high accuracy, and make the size very small. So this is what the engineers have to do. So now the question is, the guaranteed or the like a normal accuracy of GPS is about 10 meter. Okay, this is the theoretical or technically possible accuracy, 10 meter. But how can we get, or why can we get centimeter level accuracy when this is designed for few meters of accuracy? Okay, so this is where all these error correction techniques come. So you have a technology called the differential GPS, DGPS. Then you have this carrier phase processing using the RTK. Then you have a Madoka all these PPP techniques and all. So all these techniques, they remove some of the errors and give you the centimeter level accuracy. So this is already explained by in the RTK presentation and also in the Madoka, what type of errors and all. So I will just repeat few slides to give you more clear picture. Like, for example, I put antenna somewhere here and I log the data for many hours. And I don't do any error correction technique. So this is what you get. Okay, this is a 50 centimeter grid. So if you count here, it's about plus minus 3 meters of accuracy. That's about 6 meters of accuracy. Okay, so this is what we say. Okay, if you don't move, just put the antenna and log the data and don't do any error correction technique. So this is what you get. Whether you buy $10,000 receiver or $100 receiver, this is the data you get. Okay, $10,000 receiver doesn't give you better than this because this is a signal coming from the same satellite. So it has nothing to do with your receiver. Of course, some receivers, they have a very good processing technique and all. They may have a little bit better, but anyway, it looks like this. But if you do some quad phase processing or DGPS, differential GPS, what we normally say in terms of technical terminology, DGPS, then you remove some of these errors, bias and all, and then you get this type of very nice, some random errors, the scatterings here. Now your accuracy is about 1 to 3 meters here. Okay, this is the DGPS accuracy you can get from the quad phase data processing. So, okay. And these slides, these pictures are the same data. Okay, this is the same red point. We change to blue point doing a DGPS. Okay, and then further we do the RTK, and you get the green points from these red points. So here is you have a few centimeters accuracy. So this is the best possible accuracy for this data and the antenna. I mean receiver and antenna. Okay, and this data is logged by low cost U-Blocks receiver. Okay. So after we did RTK, so the accuracy you get is very, very good. But we have to do all the signal processing. Okay, and that's where you need a special software to remove all these errors. So the problem is how to go from this red point to blue or green. Okay. Some applications, they are okay with 1 to 3 meters, so you don't have to do this. So don't do it unnecessarily if you don't require, okay? Because this is a lot of work. So we can get it. Doesn't mean that you have to do it, okay? Unless your application requires. If your application can use just the 1 to 3 meters of accuracy, even if you get the 10 centimeter, it doesn't make any sense because there are so many other data that has an error of 1 meter. So even if you have error of 1 meter, so this will probably not help you. Of course, if you have this, it's better, but this will add up the cost or the processing technique. So the problem is how to go from red to green and what are the techniques for that. So this is the whole thing about this webinar using the RTK. So you can go from red to green using a Madoka. You can go from red to green. Okay, but RTK and Madoka, they have a different way of processing the signal and different requirements to process the signal. So I will repeat this slide. So Dr. Ize, so the similar in a different way. And also I think you have seen something similar in Madoka in a different slide. So this is in the summary table. So normally we have a different types of errors in the GPS signal. So these errors, some of these errors are common. Common means it's common for all the satellites and we can remove. Okay. So this is the satellite orbit error, the GPS satellite orbit error. This is the clock error, and some are atmospheric error and multipath and receiver circuit error. So these two errors we can remove completely, okay, because this is related with the satellite orbit. So this is what is done in the Madoka. Okay, so and this is a ionospheric error and tropospheric error. In Madoka PPP, we remove these errors, so the 4 or 5 meters of error is gone to 0. And in the local correction, we remove these also, so you have this is also gone, and this ambiguity resolution is very, very fast in terms of in the case of the local correction data. Okay, so that's why If you remove all these errors, so that's the reason you go from this red to green. Now you see here 2, 2, 4, and 8. Okay, you have about 6, 7, or 10 meters of error, and here you remove those 6 meters of error from red to green, because that can be done easily if we know how to do that. Okay, so this is all done by the software called the RTKLIB or Madoka or whatever. So all these special algorithms are there, and this software, they use these algorithms to remove all these common errors and minimize some of the atmospheric errors and so on. So this is the basic technique to go from these red dots to the green dot for the high accuracy. So you must have a base station, okay, for RTK. So there are different ways. So one is you put a base station at a known point, and you observe the signal here continuously, so that you know how much error exists here. Okay? Because you put a station here at a known point, so you measure here. That means you know the error here. Okay, and then you send this data, this information, correction data information or error information, whatever, all the necessary data to the rover to tell this guy that, okay, I'm here, I'm standing here for 24 hours all the time, because this is a fixed course or base station. It doesn't move. So it knows its error. And this is telling that, okay, at this time, I'm getting so much of error for this satellite, and this satellite. So please remove these errors at your site from these satellites. Okay, so this is what they are doing. And since it has some reference error information from the base station, so he knows how much error is there at that time, and those errors will be removed here. It can be done in real time. If you want to do it in real time, then you have to send the data from here to here in real time using the Wi-Fi, internet, or data modem, whatever. Okay, so you need an additional link here. Now, one limitation for this is because here is a space, the sky, and the atmospheric condition over here and over here will be similar if they are nearby. But if they are very far, say if they are 100 kilometers away, the atmosphere here and atmosphere here will be different. Ionospheric and tropospheric conditions will be different. So you can't do RTK for a very, very large distance. So I think the maximum for very good receiver and good antenna, I think the 40 kilometers is the maximum distance. Okay. Normally, it's recommended around 20 kilometers of the radius. So you can go, say, for a centimeter accuracy, or maybe 20 kilometers is the max because of this ionospheric estimation limitations. As the distance increases, your estimation gets worse. Okay? But this one requires a base station, RTK. Now to solve this problem, because this means additional cost, okay? You have to put so many stations, like in Indonesia, they have so many stations, and it requires maintenance and all. So it's very, very costly process. So every year you have to do all the maintenance, running, and all these things. So it's very costly. So how to avoid that is you send those correction data, orbit and clock correction data from the satellite itself. This is what QGNSS does. Okay, so here we are sending from base station to the rover. So here we are sending from the satellite directly. Okay, so this is the basic difference. And this one, using the Madoka or CLAS signal, there are two signals. Madoka, they send the orbit and the clock correction data, and these are received directly by the rover in the field, and then you can do the Madoka PPP. But again, one problem here is because this signal is broadcasted using a very special frequency in the L6 band and Madoka signal, which is a totally different from other GNSS signal. And today, you don't have so many receivers in the market. Just a few makers, they have a Madoka receivers, and it's quite expensive as well. So it will cost you more than $10,000 for the Madoka receiver. Again, it's a bit expensive at the moment. So what GPass company is providing is that if you can't receive from a QGNSS directly, so you receive this correction data through their server. So you can access their Ntrip server or data server, and you can get this correction data from their server to your receiver, and then you don't need this type of base station. So this is the thing. So there are two ways. Either you get the data from the satellite directly, or you get the data from the server somewhere who is providing the service. Okay, so you can do the Madoka PPP here. So these are the two basic differences between the RTK and the Madoka. So I have already. So, okay, then we have many different types of low-cost receiver systems. So one is for the RTK based on the Raspberry Pi, and this RTK Droid is based on the Android device. You can connect your u-blox receiver or other RTK compatible receivers to this tablet or smartphone to do the RTK in real time, or you can just log the data and do in post-processing. Okay. There are many different versions, but basically we are promoting this one because this is easier to use. Okay. And these are for the machines for or specific applications. So this is for the RTK. I skip this. So this is the same thing. This is the u-blox MAT. So you connect this receiver here using a OTG cable to your Android, and you log the data in real time. If you want to do in real time, you have to access the Encrypt server to get the correction data. If you want to do post-processing, so you don't need this, just collect, log the data, and you do the post-processing. And this one is for a screenshot for Android. This is for RTK Droid. And this is for Madroid, the Madoka. So we have two different types of systems. One is for RTK, one is for Madoka. We name RTK Droid and Madroid. So this is already distributed for the last 2-3 years, and we have improved a lot on this. So it's quite good now, no bugs, it's working well. This is not yet released. We are going to release maybe in early next month. It's getting quite delayed due to the hardware and other issues. Also, we will distribute these to some of the universities that we have collaboration, and we need to have a material transfer agreement. If you do that, then we can provide you hardware as well, 1 or 2 units of hardware and the software for Android or Raspberry or Windows, whatever, we can do that. Okay, these are the softwares we have. So you see, this is the test we did just a few days back in Tokyo. After some time, this I think around 15 or 20 minutes, so we get a few centimeters of accuracy, and this is quite good. Okay, not even the 15, maybe around 10 minutes like that. Okay. So these are the 3 products we have: MadPi, MadWin, MadDroid for Madoka. So Raspberry Pi version, Windows version, and Android version. So different ways of using. And this is how it looks like. Okay, different architecture. So this is the receiver size, very, very small, about 6 centimeter by 6 centimeter by 2 centimeter, 1.5 centimeter thickness. So very compact. Okay. And it can receive all the frequencies: L1, L2, L5, E5, L6, GPS, GLONASS, Galileo, Beidou, QG. All the satellites, more than 3 frequencies. And this can do Madoka or also RTK, okay, very, very small. The antenna is a little bit big at the moment. So we are making this antenna very, very small. We like a paper, very thin paper, and we put somewhere, just stick somewhere over here. So that's the reason I said that it should be less than 100 grams. At the moment, this antenna itself is about 200 to 300 grams. It's quite heavy. Not so big, but it's heavy. But this is quite good. But we don't know the performance of very thin antenna, maybe not as good as this. It can't be. But as long as it gives accuracy of better than 1 meter, it's okay for the low-cost system, because there are so many applications that need about a meter of accuracy or like that. Okay. Then you can have a very low cost, but the cost is still high, not $100 for this type of complex receiver. Okay. So this is what we have inside that this green box. Actually, there are 2 receivers inside. One is the F9P. Another is a Madoka decoder, very special receiver. Okay, then we have antenna connected here. Inside is a splitter and a USB, and you connect this to your computer or Android device or Raspberry Pi, whatever. Okay. So very, very simple. And this is how the data looks like from the receiver in the U center. You can also use U center to log the data from F9P. And these are the F9P message data. These are okay. And I want to show you the D9 Madoka. So these are the Madoka data coming from the satellite directly. Okay. The Madoka, the navigation data bits, it's coming in the binary like this. So we use this data for to do the correction in Madoka for Madoka PPP solution. And these are some sample data how we log in our campus. So this is still, it doesn't have a cover at that time. So I just put this Raspberry Pi 0 cover here. Because at the time this receiver was a bit confidential, so we don't want to disclose, but now it's no more, we can show. But anyway, we just put it here, and this is the Raspberry Pi 4 with the touch screen, and this is how it looks like. Okay, it's like a full computer. It's a Raspberry Pi, very powerful Pi 4, and you can add this receiver is connected here, and you can connect a USB drive to log the data, all the output data here, raw data, output data, correction data, everything will be logged automatically here, and you also get output and display here. Okay. So this is how we did the survey. And when we just put the power on, so the accuracy is not so good. It takes some time. Okay, few meters here, 4 or 5 meters. And as it goes down, when we take it takes more time, so the accuracy increases. By the way, this data, I think this is probably logged in the, I don't know where is it, in the Indonesia, probably Bali. I'm not sure, probably yes. Okay. So anyway, these are some sample shots, and this is for output, the screen from Madoka on Madroid. I can show you actually my, okay, let me share another window. I will stop here. I will show you my app from this Android device. Okay, I will share the screen. Now you can see my Android device. Okay, so we have a different types of applications here. RTK Droid, this is the RTK Droid. Let me show you RTK Droid. Okay. So if you connect USB, I mean you can connect the receiver either by USB or Bluetooth. Okay. So if you have a receiver that can that also has a Bluetooth, so you can connect your receiver through Bluetooth. So normally I use a USB. I connect M8T or F9P by USB, and once I connect, so you will see the list here. Okay. Now I don't have receiver connected, so it doesn't show anything, and it can select different types of data format. So if you have a U-Blocks, you select UBX. If you connect the septentrion high-end receiver or other septentrion, you select SBF. And if you use other receiver like Trimble or Novatel, whatever, you have to output in RTCM3, then you select RTCM3. Okay. So using this Android device, you can connect different types of receiver or any type of RTK capable receiver. Okay. And then you can select how you want to do. Single means you just want to log the data and standard processing, no RTK. Okay. So kinematic or static, whatever in the RTK. So select the angle, mask angle, okay. And then you set their entry setting to get the correction data. Okay. That's all. And you press the start rover, you get the RTK after some time. Okay. And this you can download from my homepage, but you need a password. So please send me email. I'll send you the password. And this password expires every year on 31st of December, and you have to renew. And we also have a new release every year to debug for bugs removing and new functions and so on. And this is the Madroid. Okay, so this is for Madoka. Again, it's same. So USB or Bluetooth connection. And then you can also select a U-Blocks, Septentrio, RTCM3 format. and you select your PPP, whatever static, kinematic, or single. So all these RTK droid is based on the RTKLIB. This Madroid is based on the RTKLIB and the program from GPass. Okay, so we call the GPass-lib. So it's basically based on the GPass-lib. So we just modify for Android or Raspberry Pi. So we didn't develop the software ourselves. We just did the system integration. And you put the antenna model, what type of antenna you are using. Okay, and also you need to give some other parameters. And then you get the Madoka correction data here. And if you want to use a local correction, so you can give a select here and use for the local correction data. Okay, so this is how we can use the Madroid. And this is very, very useful software tool. So we are still testing this one, Madroid. It's not yet distributed. We are planning to do it very soon. Okay, that's all for this Madroid and all. Now let me go back to my, how do I stop this? Okay. Oh, sorry. Let me switch back. And then I have to share. Okay. So this is how it looks like for Madoka. Okay, the settings, and you get all these sky plots and the output here. And this is one test. So we hold the antenna on a tripod and we walk very straight along these blocks. And when we look at the data, so it's very straight. Okay. And this map is very highly accurate aerial photo. Maybe I think they have accuracy around 20 or 50 centimeters, better than 50 centimeter for this one. And you can see this line aligns with this block. So this is because of the absolute accuracy that Madoka provides. So this is what Kakimoto explained. Okay? The difference between RTK and Madoka is that RTK is a relative accuracy. The accuracy is based on your base station. If your base station has a 1 meter error, so all your robot data, they will be offset by 1 meter. It will have the same error. But Madoka this is absolute. So it's related to the absolute coordinate system. Hence, whatever you get it is you can plot it directly over the map. Okay? So this is the basic difference between the RTK output and Madoka output. Okay. And this is for the Raspberry Pi. So just I'll show you some pictures. So please check this. And this you saw in previous presentation, how in the initial, so it's like this, and then at some time, so it becomes stable. And that's about 20 minutes now. Okay, you see, this is a 10 or 20 centimeter accuracy. And we did in Cairo, very, very far away from Japan. So in Cairo survey office, we set up the antenna here on the roof. And I'm using this Raspberry Pi device. This is a very small receiver here. Okay, so extremely receiver. We just wanted to test whether it works in Cairo or not, because you don't see QGSS there. Okay? The Japanese satellite is not visible, but we access the correction data from Japan. So we access the correction data from Japan. We have a GPS GLONASS receiver here. And then we did a Madoka for correcting the GPS and GLONASS observation, and we get about 40 or 50 centimeter accuracy. So we didn't have time to log for half an hour or like a long time. Okay? So anyway, this is just to show that it works. Okay, that's all. And please visit these links to get more information. Thank you very much.
Thank you very much, Dr. Dinesh. I think we have fulfilled the discussions since yesterday until today about the GNSS, RTK, and Madoka. Yeah, now is the time for the Q&A sessions. May I call our speakers for today? Do we have Dr. Sony? Dr. Sony? Yes.
Yes, I'm here.
Yeah, thank you very much for still staying with us. We have Dr. Yize.
Yes, hello,
Hi,
I'm here.
Dr. Yize. Yeah, thank you very much. And we have Mr. Kakimoto.
Yes, I'm here.
Yeah, thank you very much. And last but not least, we have Dr. Dinesh. So we already have quite numbers of questions here, even offline questions from the registration link, and as well as the online questions from the Zoom and streaming YouTube from the participants. So maybe the first questions I'm going to call for Dr. Sony.
Okay, okay.
Yeah. The question is, what is the challenge of GNSS applications and development in Indonesia? So, yeah, what's the challenge and problems maybe? Please,
Okay,
Dr.
okay.
Sani.
Okay, thank you very much. I think challenging is GNSS in Indonesia. I think in the recent time, I see the market industry also study GNSS in Indonesia increasing, and many instrument, many device already have in Indonesia. I think about the people can study in GNSS will give more benefit for the society. The challenging, I think, just we have to work hard to give benefit of the GNSS, and then collaborate with the other institution to give the benefit for society. And another thing is, for example, Indonesia is very large country. Indonesia is very large country. For example, costs in Indonesia still lack, and I think still better to give the more costs in Indonesia to get more positioning in the site or in the area in Indonesia. Maybe that's all, Dr. Lin.
Yeah, yeah. Thank you very much, Dr. Sony. Yeah, maybe we also need to fully apply the GNSS applications as well in the remote area, or
Yeah,
maybe
yeah.
to the district level, not only the national level. As
Yeah,
you
yeah.
said just now, our Mr. President said about the one map policy. Yeah. Thank you very much, Dr. Sony.
Okay, okay.
Yeah. I think there are still few more questions from the online questions just now, but
Okay.
we move to Dr. Yize first. Yeah.
Yes.
Dr.
Okay.
Yize, we have one question here. What is the possible use of RTK for the government projects like one map policy in Indonesia? I think the question is about how to apply this RTK for maybe kind of like government projects, yeah, in our country, in Indonesia, for example. Please. Is it possible to apply in Indonesia? Like,
Yes, of course, possible. But I think maybe most widely used maybe in the autonomous car navigation for companies in the future, I think. But
okay.
as for the government part, maybe I'm not very sure about some policy or status in Indonesia.
Okay.
So this may be better explained by Dr. Sony.
Yeah,
Yes.
Dr. Sony.
Sorry.
Yeah.
But I can
Can
add a few points later because we want to do some collaboration on that as
Yeah.
well. So I
Maybe
want to
the,
hear some words from Dr. Sony because
okay.
okay.
you know the policy and technology or the resources in Indonesia. So whether RTK is how can RTK help?
Yeah.
Mm.
How can
Do you
RTK
really need
like?
RTK or not?
Yeah, I think RTK is very important thing for the in Indonesia policy. For example, I mentioned about the in Indonesia in 2024 in president or government will create the high resolution or high base map in for whole Indonesia country in 2024. And for that mapping, we need the ground control point
Yeah.
GCP. And I think use RTK is very contribute for the ground control point.
Mm.
And then for Ministry Agraria Affair about the land registration, also our president instructs the land uh, have to
Agriculture.
finish, have to finish in the 2024 around 15 million parcel. I think also one of the technology RTK will contribute this finish this target for land registration.
Oh, that's very tough,
Yeah. Very tough
tough
in
work. Yeah.
2024.
But I'm not sure whether you need all the RTK survey or not, because
Yeah.
whether you really need a 2 centimeter or 10 centimeter or 20 centimeter accuracy,
Mm-mm.
because I think you have to decide what level of accuracy you want to achieve. Like
Mm.
if it is just a 30 centimeters, okay, then it's a more simpler. But if you really need the accuracy within the 5 centimeter or like that, then it's a completely different scenario. And then you
Mm.
probably need this high-end RTK survey. Okay, and that's a lot of cost because I heard that because Indonesia is such a huge country with so many islands and big
Yeah.
area, and
Yeah.
there are so many remote areas where you don't even have electricity and all power and
Yes,
the
yes.
communication. And
Yes.
RTK means you need all these infra,
Yeah.
and even to send your base station data, it's very difficult because that's what we also heard yesterday during
Yeah.
in the presentation from the EIZ that
Yes.
this data communication and sending the data is a bigger problem. So how to minimize the overall cost? Maybe you need a sort of a primary network of RTK based course station, which you already have. Probably you need maybe, I don't know, a few hundred more. And then I think you can adopt something similar to Madoka
Mm.
with a Madoka receiver,
Mm.
low cost Madoka receiver, so that you can have accuracy of about 10 to 20 centimeter. But the question is whether this 10 to 30 centimeter accuracy is good enough or not. So
Mm.
if it is, because this is very, very important and critical to
Mm.
define the requirements. If you are okay within 10 to 30 centimeter, then you can go to Madoka.
Yes, I see.
Okay, then we can guarantee that, okay, your observation, we can guarantee at a 1 or 2 sigma within 30 centimeter. But if you say, no, I need a accuracy of within a 10 centimeter with a 2 sigma, then probably you have to select something else and your cost goes up. So this definition must be made, the requirement, and then we can select, okay, this is a like a level A of a system, then level B of system, and level C of system. I think that we have to do for Indonesia.
Yes, yes.
And for like tsunami and all earthquake monitoring, you really need those type of very high-end course stations. But they can also be, price will be, can go down if we develop the special software and data processing technique ourselves.
Yes, yes. I agree with the Dr. Dinis. Is I think depend on the accuracy about the in Indonesia case. For example, for mapping, for land registration, or for another purpose. And with the GNSS, we can manage the accuracy. Okay, you can continue, Dr. Glenn.
Yeah. Thank you very much, Dr. Sony and Dr. Dinesh and Dr. Yizi as well for answering the questions. Next, maybe we move to Mr. Kakimoto. There is a questions here from Mr. Alfred Nabal from Urban Studies Department of Universitas Indonesia. The questions is when to use Madoka and when to use RTK in the applications. Yeah.
And I mean the sorry, say when do you use
When the question is when to use Madoka and when to use RTK applications. Yeah, because I think just now in your slide you did present the difference between Madoka and RTK. So what is actually the gap between the two and when to use each of them? Yeah.
When to use.
Yeah, when to use means like if I want to do the survey, shall I select RTK or shall I select Madoka? How do I decide which one is better for my application? What are the conditions or criteria to make a decision to choose a specific methodology?
So the difference of between RTK and Madoka is one is accuracy, as Dr. Dinesh mentioned. RTK accuracy of RTK 2 centimeters, accuracy of Madoka is 10 centimeters. So, but so for the survey use, I think RTK is better. But the for Madoka, it can be calculate the absolute position and does not require the reference station. So that is maybe useful to detect the cluster movement much earlier than RTK, because if we use RTK to detect the cluster movement, we need to decide the reference station. But unfortunately, most cases of earthquake, the reference station will be moved also. So we cannot calculate the actual movement. So by using PPP, we can detect the absolute movement of the station much earlier than RTK. So I think Japanese institutes, GSI, is using the PPP to detect, to provide the warning of tsunami by calculating the cluster movement very, very earlier time using PPP. Maybe that is one case of PPP utilization. That is for
maybe thank you very much. Maybe
so just to add a few points on that. So please, what Mr. Kakimoto said is that yes, PPP is a better to detect all these type of movements, okay, the tectonic movements or land movement or whatever, because when the reference station itself moves, your course moves, so you can detect immediately using the PPP technique. But using the RTK, you cannot, because what if the base station is moved, your robot doesn't know whether the base station moved or not. So you need still to do some network computation of all those base stations and then find out whether they are, which one is moving where, the vector and all. So, but don't get confused with the PPP and the Madoka, because Madoka has a different, like a Madoka PPP, Madoka AR, and also in Japan we have a CLAS. So Madoka accuracy is about 10 centimeter, 10 to 30 centimeter. So if your land is moved by 1 centimeter, so maybe I don't know whether it can detect or not. Okay, but the technology, the PPP technology itself, is a better than RTK to detect such type of, I mean, small, this how to say, the displacement. So this is what he means. Okay. And there are other applications like agriculture, the precise agriculture. So Madoka is now very widely used in Japan, and lots of field tests going on, because they need accuracy of about 10 centimeters or better. So I think Madoka PP is doing very well on that.
Better, yeah.
Yeah.
Okay. Thank you very much, Mr. Kakimoto and Dr. Dinesh. The next question is addressed to Dr. Dinesh. You explain about the radius of the Madoka. What of the coverage vertically, like monitoring the objects below water or below the land? Yeah, I think.
No,
yeah.
we cannot measure below land or below water.
Water, okay.
So what I could not understand. So do you want to do like a depth survey out in the river or ocean? We
Yeah,
cannot do that
okay.
because the signal doesn't penetrate the water surface or
I
the
see.
land surface. Okay, so we can't do
Okay.
that
So it's only above the
above the ground.
surface.
Yeah.
Yeah. Okay.
And also
Okay.
outside, not inside the buildings, because you need to see the satellites directly. We
Okay.
need a very good signal for very high accuracy.
And it's also not working within the space like tunnels.
No,
Yeah.
it doesn't.
Okay.
It
All
doesn't
right.
work. GPS doesn't work inside the tunnels. Yeah.
Okay. Thank you very
I,
much.
I think to observe the underwater, if you can use another sensor like a transponder, it will be possible. So once you can calculate the position of the kind of ship, or position of the ship,
Okay.
and using the another sensor, you can calculate the between the ship and the sea using the transponder.
Okay. So what is the
That will be possible.
Okay, that will be possible. That means we need another sensor, but
Yeah.
what is the maximum height below the water under the ship? Is there any
Maximum height.
maximum? Yeah.
I don't know the specification of
Yeah.
transponder very
Okay.
well, so
It depends on those type of sensor, echo sounder, I don't know what they call. There
I
are many
see.
different types of sensors. So
Okay. Because I think we did discuss about the possibilities of the research on detecting some of the waste or rubbish movement under the sea. Within our coastal area, because we are having this current issue in coastal area of Jakarta or Java Island, to detect the movement of those waste, the solid waste, yeah, under the water. So would it be possible? Not all.
what we can do is we can just know like the detector's position on the
Yeah.
surface of the water.
Yes.
And as Mr. Kakimoto explained, so if you have some other sensor to detect this waste, like some other underwater detecting system, there exist many different types of sensors there.
Okay.
They send some special signal, echo sounder and ultrasound or whatever. So they are used like the marine in the fishermen. They use the fish detection this system. They have a GPS on the boat and they know where is the where they can catch the fish. Okay, so
Okay.
this type of sensors exist, but GPS only give you the above the surface position data, and taking that as a reference, then you know
Okay.
where you are, but how deep is that information has to come from the another.
Okay. Thank you very much, Mr. Kakimoto and Dr. Dinesh.
But this is very interesting research or work, because now it's not only Indonesia, so many other countries, Philippines and also
Yeah,
other countries, they are doing this coral reef damage
yeah,
analysis, or this monitoring the waste flow.
yeah.
And we now am planning to make a very low cost buoy. So we just make a very, very low cost buoy and just put on the sea and collect all the data, water temperature, water, how to say, the chemical and all. So then you know how the current is flowing, okay, the water current and all this. So this type of data we can collect in the marine applications. Yes.
Okay, okay. So there's possible future projects on this using the
Yeah.
GNSS.
Yes.
Yeah.
Yeah.
Thank you very much, Dr. Dinesh. Then let's move to the online questions. We have one question from Mr. I can call the name because it's in Arabic. So this question is addressed to Dr. Sony. The question
Okay.
is how does GNSS collaborate with other technologies such as Google and satellite? And also in the case of maps of Palestine that is lost in the maps, how is the correlation of GNSS in this case? Yeah.
Okay, okay.
Please,
Thank you. Thank you, Dr. Lin.
yeah, please.
Yeah, actually, as I know, GNSS can give information about the positioning, navigation, and time, and the position on the point by point, also continuous point, and that information can be merged with the other technology to get other information with the position, information with the position. Yeah, I think GNSS can be merged with the other technology if we need information with the position. For example, GNSS can be merged with the Google Map and satellite imagery, but is important thing is for positioning, GNSS more accurate with the compared than Google Map and satellite imagery. And in the case of the Palestine, no mention in the Google Map. I think this is just the Google policy. Yes, Google policy. If you want, you can. Yeah, my suggestion, better you can add point of interest and give the name Palestine or other name about the Palestine in Google Map. We use the GNSS because GNSS will give positioning, accurate positioning. Maybe that's all, Dr. Lin. Yes.
Yeah. Yeah.
Dr. Lin.
It's more on political aspect rather than technology. Yeah. Thank you very
Okay.
much. Yeah, Dr.
Okay.
Sony. So next question, let's move to Dr. Yize.
Yes.
Yeah, this question I think is asked again. It was asked yesterday, and I think
Yes.
it's best to answer today. The question is, what is your software, and what is the specific feature, and how is the difference between the RTKLIB and your software? Is it possible to extract the objects? To extract water vapor value from the both RTKLIB and your own?
Yes. So to answer this question, I would like to share a screen. Sorry.
Please, sir.
Yes. So this is a description of my software and some features. And compared with RTKLIB, there are more functions, and it is listed here, but because it's more detailed theme, so I just list here, you can read. And so we also support PPP-AR and PPP-RTK. And we use, I think the most important aspect is we use partial ambiguity resolution compared with RTKLIB. We have a more robust AR strategy to get the fixed solution. So if you want to know more details about the features, you can check it on GitHub. And also I have, there's a file on the comparison of RTKLIB and native from the positioning results regarding PPP, RTK, and SPP, and something else. So you can check the file on GitHub. So this is my answer. And to the next one is the water vapor value. So I think maybe you want to get the troposphere delay, I think. So both of these two software can get the, we call it ZTD or PWV, predictable water vapor. You can get this ZTD value, then transfer by yourself to PWV. So I think to get this value, we should use the PPP method. So both of these two software can get the ZTD or PWV value. You can try. Yes, that's all my answer.
Thank you very much, Dr. Zize. I hope it answers the questions because this question was asked since yesterday.
Yes.
Yeah. So thank you very much. Next, we move to Mr. Kakimoto again. The question is how the Madoka system computers the orbit corrections, clock corrections, and the signal bias.
Okay, so it is a very similar method to with the satellite position, normal satellite positioning. So for normal satellite positioning, we need to receive the signal from satellite, 4 or more satellites of signal. So by receiving the 4 or more signals, we can calculate the position X, Y, Z and the clock offset of user's receiver T. So we have 4 unknown parameters X, Y, Z, and T. So that's why we need to receive the 4 or more satellite signal. So in case of Madoka, that is the same. So we are using the 4 or more ground stations, and these stations are receiving the signal from the same satellites. So that's why we can calculate the X, Y, Z, and T of the satellite. Sorry, my English is not very well, so this is my answer. This is okay enough?
No, I think it answers the questions already. Thank you very much, Mr. Kakimoto. Next one, let's move to Dr. Dinesh. Dr. Dinesh? Yeah. Can Madoka be used to monitor the ocean tides?
Oh, so I don't know under what perspective this question comes. So I don't, there are two ways, I think. One is like we use the buoy. So you put a buoy on the ocean and you measure the ocean tide continuously so that you know, you can measure it. So I think Madoka is better than RTK in that case, using the buoys. Because you don't need a base station and you can get almost real time, very precise, absolute position data. Okay, So this is, I think, Madoka is much better for this type of observation. But other way of observing ocean tide, this is still at a research level, although it's almost more than 15 years of research. So looking at a reflected signal from the sea. So this is using the GPS signal, the reflected GPS signal analysis. So this is completely different way. It's like a passive remote sensing. That's another way. So in that sense, if you're asking in that sense, so it doesn't matter whether this is RTK or Madoka or whatever. This we look at the signal. So this Madoka is a method of processing the signal or some correction data to remove the error. So probably your question is like using some buoy or some sensors on the sea and then measure this ocean tide. So in that case, I think Madoka is better compared to RTK. So you will get a real-time position data without doing any requiring any base station. And in the sea, you can't have a base station within 40 kilometers. It's not possible.
Yeah.
Okay, so for marine applications, I think Madoka is much better compared to RTK because you can't have a base station in the sea. When in the land or nearby land area, you can have it, but not in the sea. So that's another advantage of using Madoka. And this is I'm also going to propose for illegal fishing monitoring or illegal vessel, illegal boats, fishing boats control in Indonesia. It's a huge problem in Indonesia. So how to control these type of illegal things, okay?
Illegal fishing,
So, yeah.
It's a very hot issue in Indonesia.
Yes.
Yeah. Thank you very much, Dr. Dinesh. Next, shall we move to Dr. Yize again?
Yes.
There is the questions to Dr. Yize. Do we have any free and trip service? Please explain about them.
Yes, and I think the most well-known entry service is like in RTKLIB, we have STR, SVR. So we can receive data from the N-chip using this STR, SVR. And also we have, if you are doing some research relating to real-time positioning, we also use the BNC software. You can search from the internet. BNC is a very powerful tool software. It's comparable with RTKLIB. So you can, I think these two software is very famous and they are also free. So you can check it. Also, there are some other software, of course, but I recommend these two software.
Yeah, but this is also, I think the question is related with the N-trip service itself. How can I get the correction data for RTK or Madoka, whatever? So if this question is coming from Indonesia, so we have an N-trip in the University of Indonesia from our receiver. So that's one possibility. Yeah. But the problem is that if you are going to use for RTK, so you should be within 40 kilometers from University Salemba campus. Otherwise, it doesn't help you. Or you need to have a service from BIZ, because yesterday we heard that for Indonesia, they provide a free service. So you can, but I don't know whether that is for post-processing. Probably that's for post-processing because not N-trip. That will be a lot of load on that. But I am sure that there exists some free services in Indonesia.
Okay, I misunderstand.
Yeah. But also that software is very important.
Yes, just now I was talking about the software.
Yeah, service.
So if you want to know the N-chip service, for example, if you want to get the N-chip data, GNSS data, you can use the, for example, the IGS real-time service from IGS. You can search on the internet from IGS and you can apply your account. Then you can get real-time GNSS data from IGS. Also, you can get the real-time orbit and clock correction from IGS, which is very similar as the Madoka service. So you can try this free service from IGS.
And let me add one more point. So since this question came, and this is very, very important to develop the applications or to develop the know-how and the technology in any country, because basically in Asia, so we don't have much information about these technologies. So what I would like to recommend is to, why don't you provide your own entry service or your own base station? And now I'm making a prototype for a very low cost base station as well. So what we do is we put all these RTKLIB or whatever is necessary, entry and RTKLIB in a Raspberry Pi. And then we can use this low cost U-blocks like a receiver, F9P dual frequency receiver, connect to the Raspberry Pi, and you just need to put the antenna in a good location. And once you connect that to your internet, this will send the data to our Entry server. And then it will be broadcasted to all our users around the world. So if you are nearby to that antenna, so you can use this service. So this is one idea that we are having. And we already made, last year, actually, we made this prototype of the base station and set up some entry servers and all to collect and share the data. But we need the support from the interested participants who can volunteer to provide the data. But again, this has some government's policy, like from Indonesia, you cannot provide the data outside of Indonesia. So these regulations and policies, so we need to clear out. It's okay if you don't provide outside of Indonesia, but you can at least provide a service within the Indonesia or within another country like Thailand or whatever. So, but we can provide even a very low cost base station system. Also, I think there was a question about that, whether they can put a base station or not. So we can do that. So you don't have to spend maybe not a 10 or 20, $30,000 for a base station. But please note that this will be not a very high class A type of a course, but it will be like a class B or C. Okay. It's good enough for all these type of day-to-day research work, training, education, and even for a general survey that will require accuracy better than 1 meter, okay? Within 1 meter. So this 30 centimeter to 1 meter accuracy is very, very important. If you need better than 30 centimeter or better than 10 centimeter, so everything changes. Yeah.
Okay.
Okay.
All right. Thank you very much, Dr. Dinesh. One other questions that I think I'm going to combine the two questions from the SAM participant. This question addressed to Dr. Sony. The question is, could you please explain more on how GNSS work with the other devices such as LiDAR or shipborne as you shown in your slide? And he is also asking another question. This one is from Mr. Fatur Rahman. How to realize one map policy using the GNSS Madoka? I think you did explain just now in your slide as well. Please, Dr. Sony.
Okay. Thank you very much, Dr. Lin. Yes, yeah, actually, for example, LiDAR data will give information about the point cloud in that area. And if the LiDAR data match with the GNSS, it's mean will give a point cloud with the position. It is simple between the LiDAR and GNSS have the communicate maybe with the some device or communicate with the some device because they have the input output, and then if the merge LiDAR and GNSS have the point cloud and with the position. And about the Madoka for the one map policy, yeah, actually for one map policy we need the one map policy. It's mean same with the georeference, and same with the database. And Indonesia, for the georeference, we need the ground control point. Ground control point can be used the GNSS to make atau to create GCP, ground control point, for the same georeference. Maybe I'm not sure. Yeah, Madoka will give the same georeference with the in Indonesia one map policy, but the important thing, the one map policy need the the georeference, and one georeference GNSS will give the contribute for the position. Maybe that's all, Dr. Lin.
Thank you very much, Dr. Sony. Maybe this one is a final questions from us. This one addressed to UT, Tumsat, and GPAS probably. The questions is to conclude or to highlight what is your specifications of GNSS product or service for us to consider, for us or any other institutions in Indonesia to consider for any future projects collaborations. So yeah, I'm sure that you already explained just now in your slide, but what is your specifications, service or products from each of your university or your company just now from GPAS as well? Please, Dr. Dinesh, Dr. Yize, and Mr. Kakimoto. Please, Dr. Dinesh. Yeah.
Sorry. I could not grasp your question.
Yeah. What is your specifications of GNSS product or service that we could consider maybe for the future collaborations from Indonesia?
Oh.
Yeah, like just now you
okay.
You are having like Android apps.
Okay, yeah, but I also in my slide I put there's one slide. So what are your requirements? What are your applications? Okay. So based on your application and based on your requirements, the requirement is the accuracy. Your application, whether this is for agriculture, whether this is for transport, whether this is for environmental monitoring, whether this is for marine, or whether you are going to log in real time post-processing. So what accuracy, how do you log the data, whether it is logged by man, I mean people, person carrying a device, or whether it will be put on some remote area, unattended, on a machine. So based on all these, so we select the platform. It can be RTK Droid, not RTK. It can be not a Raspberry. It should be Raspberry or like that. Not the Android or not the Windows. That will be too expensive. So we use the Raspberry Pi, the cheapest one for that, for the remote operation, just logging the data, not post-processing, not real time. So this is one solution I'm now proposing to the marine research in Indonesia for the illegal fishing, something like that, the management or control and all. And for the now, I just talked with you last a few weeks back that we want to do some transport, the traffic congestion or in transport related research or work data collection. So for that, maybe Android or again the Raspberry, some device with a very low cost receiver. And then we log the raw data. We don't need the real-time data. We log the raw data, and when we come back, then we do both RTK and Madoka, all these type of different processing, and we see which is better in the case of Indonesia. So this all depends on the specification, depends on the requirements, how you want to operate, what functions you need. So, but overall, so we look for a very low price. That's the target. Otherwise, it's not possible. Okay. You can't buy $5,000 receiver 100 unit.
Yeah.
But
Especially
probably you can
urban
buy
space.
$100 receiver,
Yeah.
100 unit.
Sure. Thank you, Dr. Dinesh. So we are excited to wait for your Android applications for us to use here in Jakarta as well. Thank you. Maybe next for from Tumsat, Dr. Yize, could you please quickly discuss your highlights? What is your specification GNSS products or service?
Yes.
Yeah.
I want to, because my research is related to the just RTK or PPP RTK. So in RTK or PPP RTK, we have to consider the effect of ionosphere. And for Indonesia, because it's in the low latitude, so maybe Indonesia also suffer from very high ionosphere effect. So maybe we need to test how is the effect of ionosphere in Indonesia for RTK, and we have the course station in Indonesia, and maybe in the future, if we want to provide service like SILAS or Madoka, so we need to consider the ionosphere and how the ionosphere affect this service. So if we have GNSS data and or course station and also on the lower station, and we would like to test the effect of ionosphere. So this is from my side.
All right. Thank you very much, Dr. Yize from Tumsat. And last but not least, Mr. Kakimoto from GPAS, please.
So question is, sorry, I cannot.
Yeah.
How collaborate?
Yeah. The question is, what is your specifications of GNSS service or product that would consider for collaborations later?
Okay.
Yeah.
So
yes. Your best product.
Best product. Now we GPAS is providing the Madoka augmentation service. So the message can be received in Indonesia, of course, via the internet and via the QGSS, both communication devices. So that is most that is our product, best product for Indonesia, I think. And if you need any kind of support or consultant to for utilization of Madoka, we are pleased to propose a collaboration.
Yeah. Thank you very much, Mr. Kakimoto. Of course, we will contact you for that. Thank you very much. I think that concludes our discussions for today, or maybe for these 2 days. I can pick the highlight that for today's discussions, we can see that the alternatives or range of GNSS applications in different fields, including academics, research, commercials, and institutions. And as well as just now, the speakers elaborated about more specific about the technical parts of the applications. So thank you very much. I think, yeah, of course, we hope that it could contribute very good insight to all of us for these 2 days. Thank you again for all speakers, participants, and committee for making the success of the events yesterday and today. Again, we are happy that our CSDA is already officially launched. To all participants that are patient enough, to be with us since yesterday, three hours non-stop webinar. Thank you very much to join us. I think that's it from me. I hope we can see in the next event or programs. I'm going to pass the floor to our Master of Ceremony. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh. Very good evening, everybody.
Thank you very much.
Thank you very much.
Good evening.
Thank you, Dr. Lim Yola. To all participants, please kindly be informed that the link of attendance is already provided in the chat room. please fill in the attendance to gain an e-certificate of the webinar. Now we will have closing remarks from SSGS Universitas Indonesia Vice Director. Please welcome Abdul Mutaali, PhD.
Okay, thank you, Ms. Siti Nur Hasana. Okay, thank you, Ms. Nur Hasana, Your Excellency, Director and Deans, distinguished speakers, partners, and guests, our honored participants, ladies and gentlemen. Assalamualaikum warahmatullahi wabarakatuh. Peace and prosperity be upon us all. Very good afternoon, good morning, and good evening to some of you from some other countries. I would like to appreciate and thank you for your contribution, all speakers, partners, guests, and participants on our launching of Center of Spatial Data and Analysis and GNSS webinar series. I'm Vice Director, Dr. Abdul Mutaali, Vice Director of School and Global Studies, Universitas Indonesia. I'm grateful honor to have this opportunity to closing remark this event. After I listened to the presentation of the speakers for today's, yesterday and today, I conclude the significance of a Center of Spatial Data and Analysis for multidisciplinary research in strategic and global, national and international spatial studies. And also the center is one of strengthening of our research and in the strategic and global studies in our university. We are grateful for collaboration, for collaborating partners, University of Tokyo, TUMSAT, Japan, and invite parties such as big mapping faculties and universities from 17 countries. Center for Spatial Data and Analysis is the center that accommodates the spatial database and research program of School of Strategic and Global Studies, Universitas Indonesia, with the multidisciplinary approach. We hope we can work together because the center does not only focus on research and academic, but also project with government to government and private sectors. Thank you. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Thank you, Mr. Vice Director. Ladies and gentlemen, our program today is closing to the age. I would like to add some information about our GNSS webinar. The webinar 4 will be held next month in October. And we also have some upcoming programs. We will have 2 international conferences, ISDEMS and ICSGS. The conferences will be officially open in October for call for papers, and the conference will be conducted virtually in December. Ladies and gentlemen, you can also visit our website on www.csda.sksg.ui.ac.id. And now there's a request from the committee that we will have for a session. To all speakers, invited guests, and participants, please turn on the camera. The committee ready?
Yeah.
Baik Bapak Ibu, saya mulai hitungan ketiga ya untuk kita foto bersama screenshot. Oke, 1, 2, 3.
1, 2, 3.
Oke, terima kasih Pak Mutaali, terima kasih banyak.
Okay, thank you for all.
Thank you.
Speakers, partner, guests, and participants. Thank you for all.
Yeah, thank you.
Thank you.
So please join our future training. So this time is more introductory. So we plan to have a more exercise and training and workshop maybe very soon. Thank you very much.
Yes.